Welcome back. Having descriptively introduced the different forms of radioactive decay in the previous lecture, we will start looking at some more quantitative aspects of radioactive decay. This is an old topic starting from the early 1900s when radioactivity was first observed. People have tried to fit the data. So one of the most common way of fitting the data was, let's say you have n number of atoms which are radioactive, and the rate of change of radioactivity is proportional to n. And that constant of proportionality is specified by this constant symbol lambda. So here Dn indicates the decrease in number of atoms that are radioactive. So there was actually no particular more microscopic reason to fit the rate of change of radioactive atoms according to this law. Okay, so it was just a empirical fit at that time. But in hindsight, when you look at this law, uh, so to speak, from the point of chemical kinetics, many more microscopic things become apparent. For example, in chemical kinetics, when you have a rate law that is first order versus a rate law that is higher order, that has certain microscopic implications. So what does this suggest? The rate of change of radioactive atoms with time is not dependent on n squared. Okay, so when you say, let's say, in chemical kinetics, you may anticipate atoms colliding to form a product. Okay, so in that case, the rate law would be not of first order, might be of second order, because the rate of collisions is proportional to n times n. Okay, so that is one way of thinking about it. In contrast, whenever you have something of first order, it is like unimolecular kinetics. Uh, what is causing the reaction to happen is the question. Okay, so all the causes for the reaction seems to be more or less internal. Even if there are some external constants, let's say external radiation and so on, that may remain a constant. Therefore, that doesn't come into this rate equation. So, one way of thinking why this unimolecular kinetics might have been followed in a rate law is that there are some internal fluctuations. Whenever we talk about fluctuations, we are talking about something that fluctuates above and below a particular average. So, what is the meaning of this average in the case of chemical kinetics? There, in chemical kinetics, is more or less clear, right? So the average can be the average thermal energy, um, which is measured by temperature, let's say. So once you keep temperature a constant, that indicates only that you are keeping the average energy a constant. It doesn't mean that the energy of the molecule cannot change. The energy can be more or less than the average energy. So it's important to differentiate between temperature and internal energy. These are topics that are addressed in thermodynamics and statistical thermodynamics, but an elementary understanding is always useful. Whenever we say a temperature is kept constant, temperature can be interpreted using, let's say, equipartition theorem, where each excitable degree of freedom has thermal energy equal to half kT. So when we say temperature is kept constant, we are only referring to average energy possessed by each degree of freedom. We can only keep the average energy a constant, but the internal energy of a system can fluctuate above and below this average energy. So, what is the take home message here? Temperature is indicative of average internal energy, but at a given moment, the internal energy can be above or below this average. So, in the case of, let's say, unimolecular kinetics, you may anticipate the propensity for a reactant to go to the products is greater if the energy fluctuation is such that energy is more than the average energy. So that may give you a propensity um, to transform the reactant to product. So all these things are more intuitive in the context of chemical kinetics because we can easily identify the temperature via the equipartition theorem. When you think about nucleus or nuclear reactions, the meaning of temperature is not that clear, especially with respect to nucleons, right? So we, as I mentioned, we ascribe the meaning of temperature in most of the chemical systems um, via equipartition theorem, which depends on certain features of the Hamiltonian. That each there should be for every quadratic term in the Hamiltonian, you have half kT. These are all concepts from statistical mechanics, but the nature of the Hamiltonian for the nucleons itself is not clear. So the validity of equipartition theorem is surely not obvious in the case of nucleons in the nucleus. So the meaning of temperature itself is not very clear within the nucleus. Uh, so mind you, I'm talking about within the nucleus. I'm not referring to oscillation of the atom in, let's say, in a condensed matter. That is a different issue compared to the nucleons inside the nucleus. So these, I mean, if there are questions, we can again address this in the class. Uh, so uh, again, I'm stressing this fact, even though it was emphasized in the previous lecture. Um, Whenever there is radioactive decay, there is an energetic driving force. What we are interested in is in what governs the kinetics, which is related to the activation barrier. Okay, all these, a lot of material has been condensed into one slide. I'm sure there might be questions. We can again take it up in the class when we meet again. So it's while this is very easy to understand for, let's say, chemical kinetics, even for nuclear structure, as we saw in the um, previous lecture, there is an energetic driving force. So there is a propensity for the nucleus to change from the reactant nucleus to the product nucleus. Whenever there is a propensity for such a change, uh, we can also anticipate that the nuclear structure might show some fluctuation, okay, which are indicative of this propensity to change from the reactant to the product states. Let's move on. So whenever we talk about fluctuations and temperature, a good number to keep in mind is the value of kT at room temperature. K is the Boltzmann constant, T is the room temperature. So the value of kT is only 26 milli electron volts. Okay, so this is a good number to have in your mind. This sets a scale for all thermal fluctuations. So if the covalent bonds do not break spontaneously because of thermal energies, because the covalent bonds are between 1 to 2 EV. Okay, so the value of covalent bonds. So just thermal fluctuations cannot break a covalent bond. However, if you look at the hydrogen bond energies, they have this much, that their energy is of the order of thermal energy. So hydrogen bond can easily break just because of thermal energy, but covalent bond will not break. Compared to these energies, the energies that we see for in nuclear reactions is of MeV. Okay, so this is small m. We are talking about mega electron volts. Okay, so it's much larger compared to thermal energy available at room temperature. So another important point is whenever we talk about uh, thermal energy being stored, we are that is half kT being stored in every degree of freedom. We are talking about excitable degrees of freedom. So when you look at, let's say, helium at room temperature, it has 3 degrees of freedom because along the x-axis, y-axis, and z-axis, there are 3 translational degrees of freedom wherein energy can be stored, right? You can have kinetic energy along the x-axis, y-axis, and z-axis. However, when you consider plasma, uh, hydrogen, let's say, just as an example, let's say at hydrogen at a plasma temperature, the excitable degrees of helium is more, right? Because even electrons have been excited at these temperature. So the degree of freedom is different when you consider helium at room temperature and helium at plasma temperature. Why is this all relevant? So all this is relevant because uh, we have an energy ladder to think about degree of freedom. So the simplest are the translational degrees of freedom, vibrational degrees of freedom, rotational degrees of freedom. Then you have another at higher temperature, let's say at plasma temperature, you might be able to excite electrons, especially the valence electrons. So the excitable degrees of freedom is more compared to electronic excitation. Nuclear excitation is much more harder. So even though the nuclear degrees of freedom uh, can potentially be excited at normal temperatures which are observed, we do not really take them to be excitable degrees of freedom. So those degrees of freedom more or less are frozen. So again, all these concepts are from statistical mechanics. So if things are a bit vague, it's good to take a course on statistical thermodynamics and statistical mechanics to um, get these issues clarified. So, internal fluctuations, whenever we think about internal fluctuations, we are in a way thinking about excitable degrees of freedom. Whenever things fluctuate, there should be certain energy levels that are available for the system to reach. So, we are thinking about excitable degrees of freedom. So, when nuclear reactions are occurring, uh, what are the excitable degrees of freedom is an important question. So in a way, one can think in within the liquid drop model, when nucleus that is spherical becomes non-spherical, that is indicative of certain collective excitations. Okay, so that can be indicative of excitable degrees of freedom. So how do we quantify all these issues is a question we will try to address. Let's move on. So all I'm trying to why this elaborate um, preamble was provided is, even though this rate law, you have seen this from your high school, the microscopic reasons for this rate law is fairly complicated. Okay, so we have evaded those complications in your high school or in your introductory physics classes because we just accepted this rate law and we didn't question why this is linear in order. What is the implication of this rate law, the microscopic implications of this rate law? Once you ask those questions, um, questions of um, temperature of the nucleus, temperature within the nucleus, excitable degrees of freedom within the nucleus, all these things um, become relevant. So let's move on and let's look at the ways this rate law was first obtained? Um, Fortunately, there were some simple experiments which are suggestive of this rate law. So this can be solved mathematically very trivially. So you will get this solution. Here N naught refers to the number of radioactive atoms at time t equal to 0. N refers to number of radioactive atoms at any time t. Um, so how are these experiments done? You measure the activity of some pure radioactive compound. Um, and the radioactivity falls down. So here it's the radioactivity of phosphorus. So as a function of time, the activity keeps coming down. And how is the activity measured in times of some disintegrations? Okay, so this Geiger-Müller counters are not too expensive. Anybody can buy it. It's between 10,000 to 15,000. Many of the labs, science labs, physics labs will have it. And if you have it, you should switch it on and see. Then you would get an idea of how much background radiation is there in our atmosphere. You would hear the clicks of the Geiger-Müller counter once in a while. That is because of the background radioactive radiation that is present all around us. Okay. So Geiger-Müller counter is sensitive to not only radioactive, some form of photons. It is also sensitive to other particles too. Okay, so there are many ways of measuring um, radioactivity. So when you make these measurements, you get some such plot. So this can be fitted to this kind of an equation where A naught refers to this point, activity at time t equal to 0, and this is A refers to activity at any particular time. From this, you can also infer this kind of behavior. So there are some typical units. 1 becquerel refers to 1 disintegration per second. 1 curie is this many disintegrations per second. The need to use different units is because of variation in radioactivity amongst different elements. From this, you can easily also, once you take a log and substitute n is equal to n naught by 2, you can get t half for in the case of radioactivity. This kind of a law you might have also seen in your chemical kinetics, in the case of chemists, or in your chemical reaction engineering course in the case of chemical engineers. So this is a common behavior which is true for any system that shows this kind of rate law. It can be a nuclear system, chemical kinetic system, it can be virus behavior, biological system, and so on. So T half is an important quantity. What is important to understand is T half is inversely proportional to this constant, radioactive constant. If radioactive constant is large, that means the rate of change is large, therefore T half is less. So in this case, uh, you T half is 14.3 days. Typically, to get this kind of behavior, you have to plot in log scale, right? So if you plot the activity in log scale, because of this form of equation, you see a linear behavior, right? So in what is important to understand is in the first half-life, this much, the radioactivity has decreased from 4,000 to 2,000, right? That's what you mean by one T half. In the second T half, let's say another 14.3 days, the radioactivity has decreased from 2,000 to 1,000. Then half of that with every subsequent T half period, all right? All these things you must have seen in your chemical kinetics or chemical reaction engineering class. Just to give you an idea of the range of half-life, We looked at phosphorus. It has 14.3 days as half-life. Some half-life are even lesser. Some are much more. This is very small. All these things are very useful. Okay, radioactivity is not only uh, relevant to atomic energy generation in large scale or atomic bombs. There are a lot of usefulness of radioactivity in chemical sciences and biological sciences, okay, in health physics and medical physics and so on, okay. So it's an important area. We will see the applications of nuclear and radiochemistry in the later lectures, but um, radioactive isotopes with different half-lives are find different uses in variety of contexts. So one of the important applications of radiochemistry is to be able to produce radioactive elements of different half-lives. So, and another important point to understand is if the half-life is large, the decay constant is very small. If the half-life is small, the decay constant is large. Another way of talking about activity is specific activity. So this is disintegration per second per microgram of the material. So here the activity is specific activity is large. Here the specific activity is small. Another approach is the statistical aspects of radioactive decay. So the way to derive this is the following. The probability for disintegration to happen is proportional to the time you allow the radioactivity to occur, right? The time of observation wherein disintegration is measured. As the time increases, the probability of decay or disintegration also increases. So whenever you have this linear behavior, not a quadratic or a sublinear behavior, you can just use some constant, right? You can say P is equal to constant times delta T. So if this is the probability for decay, probability of something not decaying is 1 minus P. So if it has not decayed for lambda times delta T time segments, that is lambda delta T time, then it has not decayed for so many times, right? In each of these time segments, delta T time segment, the probability of it not decaying is 1 minus P. So if it does not decay in lambda delta T for each time segment, I mean, not lambda delta T, for n time segments, okay? So you multiply all these probabilities together, right? So this, I'm correcting myself, it's not lambda delta T. You have not decayed for n time segments. What is n here? N times delta T, that is this small time segment. N times delta T is the total time. So if it has not decayed till time T, you can discretize this time via this delta T. Therefore, there are n time segments wherein the system has not disintegrated. Therefore, you multiply 1 minus P n times. When you do that, you get this formula. You're just substituting it here, and you can use this relationship to get this relationship. All right. What have we done? We have just substituted in this case delta T as using this formula. So with this formula, you obtain this formula. So there is a simple approximation in mathematics, again, which you might have seen in your high school. This is that formula. We are going to use this formula in plug this formula into this expression and then simplify this expression in this manner. This is just ordinary simplification. Once you have this, we can further substitute, right? So once you have this formula, after, let's say, n time segments, n atoms have not disintegrated, and you started with n naught uh, atoms. So n by n naught is equal to 1 minus p to the power of n. So putting all these together, you get this expression. Therefore, you can get this formula. So what have we done? So here we have used an alternate definition. We have derived the same thing via solving the differential equation, but we have used this statistical aspect of radioactive decay. What is the statistical aspect? The central um, aspect is that the probability is independent of the history. Okay, so independent of the history, the probability has not changed. Therefore, for any time t, we can discretize in terms of some delta t, and we have attributed same probability for each delta t. Okay, so uh, these kinds of processes have some technical name in mathematics and have certain meaning in statistical mechanics. Without going into all those things, the central feature to understand is this probability is same for any delta t. It is independent of the history of the system. With that, that is an approximation, okay? And there are some basis and some implication into the microscopic mechanism. We have derived this formula, which was also derived using experimental evidence. So the last topic is the mean life. Mean life is, if you have, let's say, n number of atoms, okay, to begin with, let's say you have n not a number of radioactive atoms, and let's say you keep track of time when something disintegrates. To get the mean life, that is uh, uh, this is a quantity that is different from half life. Half-life was defined as the time taken for the radioactivity to become half of what it was at some time t equal to 0. At t half, it becomes half. But here, mean life refers to average lifetime of a particular atom, right? So how do you get the average? Because any atom may disintegrate at any time period. We just don't have a control on this. There are some internal modes which make it decay. So what do? You document the time, okay, when some disintegration occurs, okay. So, and let's say at some time segment, dn number of disintegrations occur and so on. So that is the way this formula comes about. So this is the average life of a radioactive species. Um, so how do you go about doing this? We know the some rate law obeyed by these systems, right? That rate law is given by this mathematical form. Using this form, you substitute for dn into this. Once you substitute with simple manipulation, um, integration, so on, we can get the this particular form. From this, we can also say that um, because okay, so this is a way of defining average lifetime or the mean lifetime. This has to be differentiated with half-life. Half-life was related to the radiation constant using this formula, 1 by lambda, but you define the average life using this formula. Okay, so these two are two different quantities. It cannot be used interchangeably. In the next lecture, we will look into branching nuclear decay and its half-life. That's going to be the topic for the next lecture. Thank you.